Hello everyone. Today we will start a new unit. And not just a new unit, but a very important one. The unit of quadratic relations. I always say to my students that if you understood quadratic relations in grade 10, then you will love the grade 11 math course because it's about functions. And quadratic relations are actually functions, which we'll look into it later. And all functions behave similarly, and quadratic relations gives us the foundations to understanding all the functions that are out there. So let's get started. Recall from grade 9 that a relation is a connection between two variables x and y. So when we put two variables together in an ordered pair, then we're going to say that they are related to each other. They make a relation. If you put more ordered pairs together, they will make a bigger relation. But so far, we have discussed relations in equations of linear form. A linear relation is a relation in the form y equals mx plus b, if you remember from grade 9, which I'm sure you do because you probably just finished the unit of linear systems. And this year, we'll look into quadratic relations. And quadratic relations are in the form y equals ax squared plus bx plus c. Now, the reason why we call them quadratic is because of the presence of this power here, the power of 2 squared. And in linear relations, we didn't have this power. We had a power of 1 or nothing to see there, which meant 1. And that gives, this power here gives the quadratic relation their quadratic nature. So let's take a look at a quadratic relation. We're going to look into what we call the first and second differences. There is a fancy name, a more general name for it. They're also called finite differences, but you don't have to worry about this right now. It's something you're going to look into at a deeper extent in grade 12. Okay, so here we have a relation, and in this case it is described by a table of values. So the first is x always goes first, and y is after. If x equals -2, y is 13, at -1, y 10, 0, 7, 1, 4, and so on. What we're going to do is find the first differences. If you remember from grade 9, we found the first differences in linear relations, and we noticed that the first differences were constant. If you don't remember that, don't worry about it. Now, how do we find the differences? Now, one thing I want to emphasize here is the importance of subtracting the previous term from the term after it. So what that means is, when we find the differences, we go second minus the first. So the same thing with the next pair in here. So we go second term minus the first term. The next pair, the same thing, the second term minus the first term. So we don't go the other way around. So we always go what comes after minus the previous, okay? This is very important, by the way. The same thing here, 1 minus 4, -2 minus 1. And since I'm here, I'm going to find those values. You probably notice that we kind of end up with the same difference here, -3, -3, and -3, -3. When first differences are constant in a relation, we say that the relation is linear. So that's like a confirmation, all right? If you were to find the second differences, which again, it's possible to because we do have y values here, we are going to say that in this case we have -3 minus -3 equals 0. Again, -3 minus -3 equals 0. And you don't want to be annoyed by me going over all of these because you see that the second differences are 0. This is very typical in linear relations. Now we're going to take a look at another relation. And here we have, again, a similar chart. So here goes x, here goes y, and we're going to find the differences. So in the same way, it's the same fashion. So again, we subtract the first from the second, which means we go 12 minus 27, 3 minus 12, 0 minus 3, 3 minus 0, 12 minus 3. Okay, and now let's calculate them all. So 12 minus 27, if I'm not wrong, is negative 15. And then 3 minus 12 is negative 9. 0 minus 3 is negative 3. 3 minus 0 is positive 3. And 12 minus 3 is positive 9. As you see in here, our first differences are not constant. So therefore, we're going to say that the relation is not linear. So we're going to call it a nonlinear relation. But we don't want to stop there and just call it just nonlinear. So if it is not linear, are there other patterns that we need to discuss? And that's why we go for the second differences. So again, we find the second differences the same way. So I'll subtract the first from the second. Negative 9 minus negative 15. Negative 3 minus negative 9. 3 minus negative 3. 9 minus 3. And let's see what happens here. Negative 9 minus negative 15, that's 6. Negative 3 minus negative 9, that's negative 3 plus 9, 6 again. 3 minus negative 3, 6. 9 minus 3, 6. So we ended up with same second differences. When this happens, then we're going to say this relation has some quality, right, that needs description. And the quality or the description that we give to this relation is a quadratic relation. And now I'm going to show you something a little bit fancier. Well, not really. Now, when the first differences are constant, we call the relations linear. Now, a linear relation is also known as a first-degree relation. And that's because x is raised to the power of 1. Now, when the second differences are constant, so again, second differences are constant, then we say that the relation is of second degree. So we'll say that it is, for second differences constant are typical for second degree relations. Okay? Okay, so let's move on to the next part. Now, as I said, that described a quadratic relation, and we saw them from the finite differences or second differences perspective. Now, what do their graphs look like? If you remember again from grade 9, so I have to repeat this word so often whenever I explain things in math. If you remember from that time, it's like telling a story. But the thing is that in math, whatever you learn in the past, you have to use it in the future. So math is all connected. So we are going to move on now to the graph of a quadratic relation. And here I will introduce you to the simplest form of a quadratic relation, which is y equals x squared. And together, I'm going to make this square very perfect, actually, a rectangle. So, and together we are going to graph this. Now, if you remember again from grade 9, when you graphed the line for the first time, you built a table of values, you gave x some values, and you found the corresponding values of y, and you graphed it. That's how we graph any new relation that we learn, and you are going to learn and explore a lot in high school. So, we are giving x some negative values, some positive values, and 0. And we will find what the values of y are. So y equals x squared. When x equals negative 3 will be negative 3 squared, so that's 9. So the first order pair we have to graph is -3, +9. When x equals -2, we have -2 squared, -1, -1 squared. X equals 0, that means 0 squared. x1, 1 squared, x2, 2 squared, x3, 3 squared. And this is the beauty of math, actually. When we investigate things, very often we kind of do the same thing repeatedly, and that makes it easier for us to move on and understand better. So -2 squared is 4, -1 squared is 1, and then 0, and then 1, and then 4, and then 9. And now I can put them in order pairs. So x was -2, y was 4. So -2, 4. -1, 1. 0, 0. 1, 1 again. 2, 4. 3, 9. So let's place all these points on the grid. Here we have a beautiful graph. I'm going to label the axis, the x and the y, and I'm going to let 1 square equal 1 unit. So here goes 0, and we have 1, 2, 3, 4. I'm not going to go higher than that. -2, -3, -4. And here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm not going to go higher than that. So let's plot the points together. When x equals -3, y was 9. So here we go, -3, 9. When x equals -2, y was 4. At -1, y is 1. At 0, 0. At 1, 1. At 2, 4. At 3, 9. And now I will connect the points. You see, they don't make a straight line, right? So we're going to be very gentle and draw the line nicely. It's kind of curvy. I'm going to try my best here. Don't make fun of my drawing. Here we go. And obviously the 2 arrows on the ends of the graph indicate that we can continue drawing the shape forever, but we don't want to. So this shape actually has a special name, and you probably have heard before that this is called parabola. Some people like to call it parabola, but you know, it's not even an English name or word. So now we're going to talk about the features of the parabola. I would say this is a symmetrical shape, because what repeats on one side of the y-axis, I mean what's on one side of the y-axis repeats on the other side as well. And because it is a symmetrical shape, there is some pattern that we can actually discover or talk about in here. Now, we are going to start with a very special point on the parabola that is called the vertex. And the vertex of the parabola is this very special point right here at the very bottom of it, the lowest point of it. The vertex of this parabola is at the point with coordinate 0, 0. And very often you will have to identify the vertex of the parabola. Now, the step pattern, what does that even mean? Now, when we discuss a step pattern, we start from the vertex and we think, when I graph the parabola, I used these points. I'm going to make them more visible to you. Okay, so I'm exaggerating them a little bit. And how many points did we use in here? Well, 7. So here we go. 1, 2, 3, 4, 5, 6, 7. And we're going to say, starting from the vertex, which is where the parabola actually marks that line that shows the symmetry of it, right? So if I'm at the vertex, how do I go to the next point that I graphed? So I would say that to go to the next point, I had to run 1 unit and rise 1 unit, okay? So to go from this point where I've landed already to the next one, I have to run 1 unit, and this time I rise 3 units. To go to the next point, I have to run 1 unit and then rise 1, 2, 3, 4, 5 units. You probably have noticed, or maybe not, that every time or all the time we run over 1 unit. So horizontally we move 1 unit, but vertically we go 1 unit first time, 3 units second time, 5. So there is sort of a pattern here in how we rise. So 1, 3, 5. And if I asked you the question, well, if you were to run again, how many units do you have to rise? Then you would say, maybe I don't know, but maybe you're thinking 7. 1, 2, 3, 4, 5, 6, 7. And you know what? I am going to give this a try. So if I ran 1, I would go at x equals 4. So 4 squared is 16. Is this 16? So 9, 10, 11, 12, 13, 14, 15, 16. So when we rise, we follow the pattern of all odd numbers. So the step pattern, we're going to say, every time we run 1, you move. So every time you go over 1, you go up 1, 3, 5, 7. So you just follow all the odd numbers. The same thing happens when we move on the other side of the parabola. So you move over 1, up 1, over 1 to the left, up 3, over 1 to the left, up 5, and so on. So the same pattern repeats. So every time you move over 1, we rise by following the pattern of all the odd numbers. Now the next thing, or the next important feature of the parabola, is what we call the axis of symmetry. So the axis of symmetry is the line that divides the parabola into 2 equal parts. Okay, so it will be the y-axis in this case. All right, I will call this AOS, not SOS. All right, so the axis of symmetry, we're going to say, is the y-axis. And sometimes you will be asked to write the axis of symmetry as a formal equation. And because it's a vertical line, then you can write the equation as x equals, that's the format of any vertical line, x equals a number. And the number x equals, in this case, is 0 because it's a vertical line that crosses 0. Okay? Oh, there you go. So I have asked this question next. Sorry about that. So there we go. So another thing we're going to want to talk about is the domain and the range of the parabola. To determine the domain, I always think, can I use a negative value of x and still be able to find y? Well, I did use negative values and I was able to find y. So I would say, yeah, it can be a negative number. X can be negative. Now remember, domain is all the x values, right? And then I think, can x equal 0 and then I still be able to find the value, the corresponding value of y? And I say, yeah, there were no, obstacles there. And if x is positive, I can find y. So I would say that x can be any real number. So the domain then would be any real number x. Now remember x, this symbol here, like a letter E, a funny E, means belongs to, and the capital R means a set of real numbers, which means any number that exists out there. Now for the range, we're going to look at the values of y. So as you see in here, when x was negative, y was positive. When x was 0, 0. When x was positive, still positive. So I'm thinking, what if x became even more negative? Would y be negative or positive? Well, take x equals negative 1 million, you square it, it's positive. So we're going to say that the y values always stay positive. So we're going to say y can be any real number because it's true, it can be a decimal or irrational. But there is a condition, though, which we indicated by this line in here. This line, by the way, in case you don't remember it, means such that or under the condition that such that y is bigger than 0, so positive, or equal to 0. That's the range of the parabola. So we are going to take a couple of examples together and try to analyze the quadratic relations given. So on the grid above, so on the same grid that we had in here, we want to draw the graphs y equals 2x squared and y equals half x squared. So I'm going to use a table of values still because I'm not very skilled at drawing the parabola very fast, but you will be very soon, trust me. So we have when x equals -3, then y will be 2 times -3 squared. X -2, 2 times -2 squared. And then 2 times -1 squared. 2 times 0 squared. 2 times 1 squared. 2 times 2 squared. And then 2 times 3 squared. Now 2 times -3 squared, that's 9 times 2, 18. 2 times -2 squared, that's 2 times 4, 8. 2 times 1, 2. 0, 2, 8, and then 18. So let's draw this graph. I'm going to use a different color, and if you don't mind, I am going to erase the step pattern in here because the graph is going to look pretty crowded if I didn't. Delete this. Sorry about that. Just bear with me. So sometimes the shorter way ends up being a bit longer. I'm going to redraw the parabola y equals x squared very quickly. It shouldn't be that hard. And you know what I'm going to do since we're here? I'm going to move over 1, up 3, over 1, up 5, because I know the pattern now. I'm a bit smarter than I was a few minutes ago. 1, 2, 3, 4, 5. Okay, this will be over 1, up 3, over 1, up 5. And this is how much I see, how much of a parabola I see from x equals -3 to x positive 3. So I'm going to do 2x squared now. What color do I want it to be? Let's check and see what we got in here. You know what? I'm going to make it orange. Or maybe this one here. Okay, so when x equals -3, y is 18. And remember that right here we are at 9. So 18 means that we have to go 9 higher. So 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 is right here. So when x equals -3, y is 18. At x -2, y will be 8. At x equals -1, y will be 2. At 0, 0. At 1, 2. At 2, 8. So we see the same thing. I can even just go to the other side of the y-axis, right? Because I now know that parabola is symmetrical. Okay? And now I'm going to connect all the points. And let's see what good job I'm going to do here. And I'll connect this together, and these together, and this together. Not the prettiest parabola out there, but I don't think I can do a better job than this. It's not easy writing on a screen, actually, which I am right now. So this is y equals 2x squared. And another habit we have to get into is the habit of labeling our graphs by their equations. Okay? The next graph that we want to draw is 1/2 x squared, but we have a couple of questions we want to answer in here. What is the vertex of y equals 2x squared? We're going to say the vertex is still at 0, 0, so 0, 0 it is. Now, what is the step pattern? So the step pattern is starting here from x equals 0, 0. And then as we move over 1, we have to go up 2. That's interesting. Over 1, up 6. And then over 1, up 10. Okay? So we're going to say that the step pattern is, where are we here? So the step pattern is 2, 6, 10. And the next thing we want to identify the axis of symmetry. That's the y-axis still. And the equation of it is x equals 0. And now let's do the last graph. The graph of 1/2 x squared. So for this, we're going to use color green. So that means we have 1/2 of -3 squared, 1/2 of -2 squared, 1/2 of -1 squared, 1/2 of 0 squared, 1/2 of 1 squared, of 2 squared, and 3 squared. So we're getting used to the idea that we're getting some patterns in here, so the numbers will repeat, right? So that would be 9/2 or 4.5. This would be 4/2 or 2. That would be 1/2 or 0.5. I'll write decimal forms in here because we have to plot the points. Then we have 0, 0.5 again, and then 2 and 4.5. So we'll say that when x equals -3, y equals 4.5. So at -3, 4.5. 1, 2, 3, 4, here, right here. Okay? And at -2, +2. At -1, 0.5. At 0, 0, and the other side, we know what to do because we know the drill now, right? And at 3, 4.5. So I will connect the points. And here we go again. We got another parabolic shape, but not exact same shape as the previous two graphs, but we kind of expect that. So the vertex, we'll say, is still at 0, 0. And now let's take a look at the step pattern. So from 0, 0, you go to the next point that you plot in here. That's 0.5. Then over 1, you move 1.5. Over 1, and then you move from 2 to 4.5. So that would be equal to 2.5, right? So we're going to say that the step pattern is 0.5, 1.5, 2.5. Now another way of writing these numbers is 1/2, 3/2, 5/2. And as a matter of fact, I will just erase this because these fractions look pretty cool in here. And you probably see what I mean, probably, because the reason I like them so much is because the pattern, the normal pattern 1, 3, 5, here is divided by 2. And why do you think that is? Because x squared is divided by 2. And the same thing happens in here. So the normal pattern 1, 3, 5 has been multiplied by 2. So we have 2 times 1, 3, 5, which is 2, 6, and then 10. Okay? So the axis of symmetry is still the same at x equals 0, right? So we're going to say it's the y-axis, so x equals 0. All right? And I'm going to write this a little bit better here. Sorry. 1/2, 1/2, 3/2, and then 5/2. So a few things that are observations that we want to make in here is the basic parabola, which is the pink parabola in here, has a height of 9 units for the given domain, right? Because we know we can continue forever. How about the 2x squared? Well, it's 2 times taller. How about the green parabola? Well, it seems that the height here is at 4.5 compared to 9 for the basic parabola, so that's 2 times shorter, okay? So we say that if we place a number before x squared, the shape of the parabola will change. If this number is bigger than 1, it will make the parabola stretch, okay? So it will make the parabola taller than x squared. And if the number is less than 1, it will make it shorter than x squared. All right? Y equals x squared. And by the way, we refer to y equals x squared as the basic parabola. All right? Now, we're going to move on and let's see what we have on the next page. We're going to see the last, probably the last example, which is placing a coefficient right before x in here that is negative in sign. What's going to do to the parabola? We're going to see something really cool in here. So if x equals -3, we are going to say that, and we're going to go purple this time. So x will be -1 times -3 squared, -1 times -2 squared, -1 times -1 squared, -1 times 0 squared, and so on. And let's evaluate all these numbers. So we have -1 times 9, -9, -1 times 4, -4, and then -1, and then 0, -1, -4, -9. So let's draw the graph of it. See how we have all the y values, though negative. So we have to be smart when we draw the axis. So here I am. I am going to give myself plenty of room into the negative numbers. And I'm going to draw the horizontal axis right here. And for the vertical axis, I'll keep it in the middle. Why not? And now we are going to plot our points. Here goes our purple. And we have the x and the y axis right here. And we're going to let 1 square equal 1 unit. So this is 0, 0, 1, 2, 3, -1, -2, -3. And now when x equals -3, y was -9. 1, 2, 3, 4 negatives. 5, 6, 7, 8, 9. So -9 and -1. So -3, -9 is right here. -2, -4 is right here. This is -1, 1, and so on. Now, you see that it's kind of easy to draw a parabola once we understand it. So it's a symmetrical shape, right? So here I'm going to connect them. I'm going to actually kind of cheat a little. I'm going to make the pencil a bit thicker. So it covers more mistakes that I make. Here we go. And there goes the parabola. Well, is it a parabola really? Well, it is, right? The shape is still there, and I can see it. The only thing that actually is different and surprising is that the parabola has turned upside down. And we dedicate this change in the direction of the parabola to this coefficient before the x squared term. So this coefficient is the one that made the parabola turn upside down. In this case, we're going to say that the parabola opens down. Oopsie. So what happens when parabola opens down? How do the features of the parabola reflect this change? Well, the vertex still at 0, 0. The step pattern, let's take a look at the step pattern actually. So we have moving over 1, down 1, over 1, down 3, over 1, down 5. Let's move over 1 on the other side. We expect the same thing. And then down 5. So we're going to say that the step pattern, every time we move over 1, we have to go -1, -3, -5, okay? And you can probably tell that this coefficient, this negative coefficient, is what made the step pattern different, because we already had 1, 3, 5 in the basic parabola. So the axis of symmetry is still the y-axis. The equation of the axis of symmetry, x equals 0. For the domain, we're always going to say x any real number. So if you ever have a question on a test asking you for the domain, it's a no-brainer. Just say any real number, okay? You don't have to think hard. For the range, though, we have to be careful, because for the range, we have to say, well, it is any real number, just to indicate that there is an infinity number of numbers, actually, okay? But there is a condition, and the condition in this case would be all the y values are negative, and not only that, but also 0. So we're going to say less than or equal to 0. On the grid above, we want to also draw the graphs of y equals -3x squared and -1/3 x squared. And you have probably realized by now what is going to happen. So we are not going to use the chart in this case. You can do so. You have the handout, so you can try it on your own. But I want us to kind of guesstimate what's going to happen. Remember when we had the 2 in here, then the parabola was still actually, there must be, I have to make a change in here. What I meant in here is negative, okay? Just like in the questions. It's okay, it's very easy to fix, all right? Now I'll pretend it never happened. And then we're going to say, when we had a number 2 in here, the parabola became taller, but it was opening up, so arms towards the sky. Now, when it's -3, it will still get taller, but it will go down. So the step pattern will change. And the step pattern will become now from 135 multiplied by -3. So it will become -3, -9, -15. For the vertex, it's still going to be at 0, 0. That's because when x equals 0, y equals 0. And when we actually multiply x squared by a number, vertex didn't change. And so was the axis of symmetry still the same, which is x equals 0. Now, for the -1/3x squared, we're going to say similar things about it. And we're going to say that, let's go orange. We're going to say that the vertex will still be at 0, 0. The step pattern will be from 135 to -1/3. So it's going to be -1/3, -1, -5/3. Axis of symmetry is still the y-axis, and equation of the axis of symmetry will be x equals 0. So when you draw y equals -3x squared, which we chose it to be green here, then the vertex will be the same, but we're going to move over 1 from here, here. So over 1, we're going to go 3 units down. Over 1, we're going to go 9 units down, and so on. So let's do this. Over 1, down 3. Over 1, down 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And we don't have 15, so we're just going to leave it there for now. Right? We'll extend it. We know that it's going to be 3 times as tall if we went as far as x equals 3, right? So this will be -3x squared. -1/3 x squared will have a height 1/3 of the purple parabola, so 1/3 of -9, okay? So it will be at x equals 3, it will have a value of 3 right here, negative 3 actually. Okay, so let's do it with the step pattern. So over 1, down 1/3, over 1, then down 1, and over 1, down 5/3. And this will be the graph of negative third. Okay. It will be 3 times as short as the